Hello everyone, my name is Bingyong Guo. I'm with the Center for Ocean Energy Research at Maynooth University, Ireland. Today, my topic is about on energy transfer of parametric resonance for wave energy conversion. In this talk, I will briefly introduce the background of parametric resonance and its modeling method, and also the influence of initial conditions and the nonlinear damping terms will be introduced as well. The main topic of this paper is about how the energy transferred from one degree of freedom to another. At the end, some conclusions will be drawn. Parametric resonance occurs occasionally in ocean applications for ships. It is always viewed as a negative phenomenon. This figure gives a good example. On-deck containers were hugely damaged by parametric resonance in law, hence it caused huge economic loss as well. Sometimes, parametric resonance in law can even cause a caption of a ship. For wave energy, parametric resonance occurs as well. Here, a good case study is the spar buoy. In this video, you can see the buoy heaves and pitches gently, and the parametric resonance is not on set. In this video, you can see the parametric resonance in law is on set. In this video, you can see the parametric resonance in law and the pitch is on set. In the literature, some people say we can make use of parametric resonance to harvest more energy. Also, some people say that onset of parametric resonance reduce the power observed from waves. Here is the reason why we get into the energy transfer of parametric resonance. To model parametric resonance, Maxwell's equation is generally used. Here gives an example of parametric resonance in law. C is the linear damping, and this part is time-varying stiffness term. Theta is the frequency condition, and epsilon is the amplitude condition, which can be used to describe the onset conditions. In this figure, parametric resonance occurs in these shaded regions. Maxwell's equation also gives a good explain how parametric resonance occurs. As the buoy heaves, the metacentric height changes, which may produce unstable buoyancy. However, in Maxwell's equation, it assumes that the heave motion is known, and it only can describe how heave influences law or pitch. Thus, a model of multiple degrees of freedom is required to describe such a mutual coupling between heave, pitch, and law. For buoy oscillates in heave, law, and pitch. Its linear model is given here. Well, Fe is the excitation force, Fr is the radiation force, Fhs is the hydrostatic force, and Fpto is the control force. To represent nonlinear parametric resonance, the nonlinear modeling method, considering nonlinear fluid Crylov force, is applied here. In a nonlinear model, the excitation force is divided into two parts, including the dynamic nonlinear Fk force and the linear deflection force. The hydrostatic force is also divided into two parts, including the static nonlinear Fk force and the linear gravity. In addition, the viscous force is also considered. Otherwise, the system is unstable when parametric resonance occurs. In this study, the method developed by Giuseppe and Ringwood are used here to compute the nonlinear Fk force according to instantaneous wetted surface. This method is quite complex, but very efficient in computation. Readers are referred to this reference. Based on the derived nonlinear model, parametric resonance is studied numerically. This figure shows the influence of initial conditions on parametric resonance. In A, the heave displacement is shown. In B, the law displacement is shown. The red curve represents the results without parametric resonance. The initial heave and the law displacements are zero. The black curve represents the results when resonance occurs. Here, the initial law displacement is 0.1. Such a small change in initial condition results in totally different dynamics. So we can see parametric resonance is very sensitive to initial conditions. In addition, this figure also shows that the nonlinear FK modeling method is capable to represent the parametric resonance and the bi-way coupling between different degrees of freedom. In this figure, the nonlinear viscosity force is not considered, and only the linear damping term is considered. Here we can see the heaving motion and law motion goes to infinity as time increases. Thus, it is important to consider some nonlinear damping to stabilize the system to make results more real. Therefore, the viscous forces should be considered and can be considered as quadratic terms according to the Morrison equation. The viscous coefficients CD can be selected empirically in this study. They are configured as 1, 0.7, and 0.7 for the heave, law, and pitch motion. In this figure, the heave displacement is given in A, the law displacement is given in B, and the pitch displacement is given in C. The red curve represents the results without viscosity. In B, the law displacement without considering the viscosity goes to infinity and the motion is unstable. By considering the viscous force, as shown in the black curve, the law motion is stabilized. Now let's get into the energy transfer problem. Figures A, B, C give the captured energy in heave, law, and pitch modes respectively, while the total captured energy is given in figure D. In these figures, the blue curves give the results of linear model, while the red curves give the results of nonlinear model without parametric resonance. When parametric resonance occurs, the results are given in black curves. Comparing the linear and nonlinear modeling, the captured power for nonlinear model is slightly less in heave, and no energy in law, and much less in pitch, and slightly less in total. When parametric resonance occurs, the captured power is slightly less in heave. Very interesting, it is negative in law and slightly more in pitch. In total, the captured power is slightly attenuated by parametric resonance. In terms of the converted energy by PTO systems, the results are given in figures E, F, G, and H respectively. Compared to the linear model, the convoluted power by nonlinear model is much less in heat and in pitch, and also in total. However, there is no energy converted from the raw motion if the parametric resonance is not on set. When parametric resonance occurs, the converted power is slightly less in heat and pitch. However, it is much more and positive in raw, which makes the total converted power is slightly bigger. The callback to the captured power in raw is negative, but the converted energy in raw is positive. Definitely, there is some power comes from other modes into the raw mode. To sum up, the nonlinear modeling method considering nonlinear FK force and viscous force is effective and efficient to represent parametric resonance. Parametric resonance is highly nonlinear and sensitive to initial conditions. Numerical results shows that different modes are coupled mutually and energy is transferred from heat to raw. Future work should be focused on controlling multi-stability of the system to switch the dynamics from one orbit to another, and quantitative analysis of power flow when parametric resonance occurs. Special thanks are given to the European Commission as the project is funded by the Marie Curie actions. Thank you very much. Any questions?